I am Geoffrey Mboya. I'm a student of Balash Sendroy. I'll be talking to you about uh, projective vibrations which result from bigrated rings and how we can construct some of these vibrations from bigrated rings which result from them. And this potentially could be a way of forming uh, many of these vibrations. As a motivation, I will introduce an object called scrolls. G will be a 2 torus, and lambda mu will be a general element in the group. Omega shall be the lattice of characters of the group G, and theta is the dual, it's dual. And we can see that that through the pairing map defined below the slides. Scrolls can be defined as follows. Let A, B, and C be n tuples of integers, and S be a coordinate ring of the scroll, which is bigraded and generated by variables ti, or by degree ci0, and xj, or by degree minus aj bj. L is the sublattice of omega, which is generated by the bidegrees of ti and xj. So a rational scroll is associated to a weight matrix A, where the weight of ti is ci0 and weight of xj is ajbj, is defined as a quotient of the product of punctured affine spaces ck and cn by the group G, where the group G acts by 3, the maps shown using 3. A summary of this is as follows. So Q is the quotient map that you've seen, and projection to the first factor is such that the lower horizontal map is compatible with the weighted sister action on affine CK space with weight CI. The map pi is defined by taking the homogeneous coordinates in the base, and its fibers are weighted projective spaces of weights bj. We say a scroll is straight if ci and bj's are all 1, and that it is of type n minus 1 k minus 1 if it is a pn minus 1 bundle over pk minus 1. Marco studied Calabi-Yau threefolds of Picard rank 2, which are embedded in scrolls of type 1, 3, 3, 1, and 2, 2. So these are the places where you can find some of these nice objects. Alternatively, you might have met scrolls before as weighted projective bundles. So consider a general base B and a locally free sheaf epsilon, which is direct sum of EIs, where EIs are having local weights BI and of rank NI. So consider the sheaf of graded algebra S as shown. So by taking the proj of S, one obtains the scroll, and the fibers are weighted projective spaces of weight BI to the NI. Line bundles on scrolls are defined as sheaves L chi, where chi is a character of the group G. So, and sections of L chi are polynomials over an open set V in Z, which respect the action that we defined earlier. This can be extended globally. So a global section of a line bundle L chi are polynomials which satisfy the action that we defined, and which are defined on the product of affine spaces, punctured affine spaces, CK and CN. I denote L and M to be the line bundles associated to the characters 1, 0, and 0, 1 respectively. And these are the ones which uh, are the basis of the picket group of the scroll. And the sections of this line bundle L10 is the generated by um, variables in the base. And the sections of M L10 is the direct sum of the product of xj and the polynomials of degree aj in TIs. And generally, a line bundle associated to the character D1, D2 is uh, obtained by getting the direct sum over weighted partitions of D2 with fixed weights Bj, uh, and these are polynomials of degree this sum, and remembering that all the TIs are also having weights Ci. Then we get the product over all partitions of D2, weighted partitions of D2 of xj's. So we shall call the map pi we saw earlier as the scroll map, and if we restrict this map to x, some subvariety, or in the linear section of P1, P2. So in this case, I call L and M the pullback. So I slightly change the basis of the picket group to be the pullback of line bundle on the base and an ample line bundle on X, which is also ample on the fibers. So that is our X, and then B is a subvariety of the base. Using this, we have that we can obtain the bigraded ring of the bipolarized variety X with the polarizations, the pullback of D and H as defined here. So this sum is taken over Z2, the lattice of characters of the group. So from this, if we take VIs to be the algebraic generators of R, and R1 as sub ring of R generated by UIs, which UIs are also variables of by the Ci0. Then we have surjections from S1 to R1. S1 is the coordinate ring of the base, and R1 is as defined earlier. Then we can also extend this to S1 and R as shown in this diagram, from which we get this diagram where these fibrations F can be seen as living inside the scroll map by just taking the restriction of pi on some X, subvariety of F, the scroll, and X could be taken as before to be in some linear system of some ample line bundle. So also using from the classical algebraic geometry, we also know that from this scroll, we can get a rational map to the projectivization of the P1, P2 by graded pieces. And from this, someone can study the birational geometry of the total space using this rational map. Related to our study is also the work of Miles Reid and his student Mendes Lopez, where they studied relative canonical algebras of pencils of homogeneous curves, and the object of their study are usually the relative sheaf of rings defined as follows, and the assumption is usually that the base is small, quasi-projective or affine, and the study is usually restricted to a small neighborhood of a point in be a tibial neighborhood of a point in the base. If the embedding codimension is low, then some of these fibrations can be studied using explicit methods. For instance, if you take an ample line bundle on surface scroll, then the curve in this linear system of these line bundles are going to have genus given by this formula. A type 2 scroll weights 210 with P1, P2 some positive integers such that the line bundle L P1, P2 is ample, and with the assumption that P1 is positive and P2 is at least 4, then X is a threefold of general type, which is fibered by a family of plane curves of degree P2. And up to sign, the polarization degree of X, Kx cubed, is given by this formula right here. An important and typical relative key variety where these scrolls live in is the Grassmannian fibration. So Grassmannian fibration Ga to pi, slightly changing notation to Ga. So Ga here is defined as follows. So want this pi to be Grassmannian, as fibers to be Grassmannian, weighted Grassmannians. So weighted Grassmannian is the quotient of cone over affine Grassmannian by torus action, where the affine Grassmannians are defined by maximal Pfaffians of a 5 by 5 skew symmetric matrix, and the weight of matrix M is given by taking the sum of weights on C5, Wi plus Wj plus some constant rational number k, which makes them positive. It could also be 0 if these weights are such that these sums Wi plus Wj are already positive integers. So using this, I define G as, so I change the last affine, punctured affine space by a cone over Grassmannian 2,5. Then I remove some closed locus. And then I take this quotient of this product by a sister co-sister action, whose with weights 1, 0 on Ti and T1 and T2. And on Xij, we have Bij and Wij. So Wij are the weight from the weight matrix that you've seen in the previous slide, and Bij are a general point on the affine Grassmannian. So using this, we have that pi is weighted Grassmannian fibration with fibers weighted Grassmannian 2,5, and taking a general element in the anticanonical class of Ga, then we have Calabi-Yau varieties fibered by K3 hypersurfaces in weighted Grassmannian 2,5. A larger class of this kind of objects, Calabi-Yau varieties fibered by K3 hypersurfaces, have been studied by Moulet. Studied Calabi-Yau hypersurfaces which are fibered by Calabi-Yau threefolds and using toric tools. And a former student of my supervisor, Alan Thompson, also studied models of threefolds which are fibered by degree 2 K3 surfaces. So my job in my research is to understand the resolution structure of this bigraded ring, with the hope that from this study we'll get geometric information about the fibers. Now the fibers of interest will be those which have some fibers which are singular. So we'll be interested in studying that kind of fibers. And some recent study by Imran on models of log del peso surfaces have found that there are eight biregular models of log del peso surfaces, and he found correct weights on the Grassmannians that are supposed to give us this log del peso surfaces. So using this and the setup that I have explained, we can get fibrations with fibers log del peso surfaces with the rigid singularities. I'm also interested in constructing moduli spaces and studying stability conditions on them, GI stability or other form of other definitions of stability on fibrations. I was interested in learning the works of Devan and Sexton, who have studied using differential geometric tools, stability on K stability, polystability on fibration ability, and some of their conjectures on whether on the possibility of constructing these moduli spaces can be solved using this setup. I believe. So I'm also interested in computing invariance in families of these vibrations, especially those that result from weighted Grassmannian vibration. Thank you.